All right, good afternoon, everyone. Thank you for coming to our session. And I know this second day, so many people maybe start leaving, but thanks for stopping by. So in this session, we are going to talk about supply chain attack and our approach to how to improve the supply chain security. I'm Ji-Young from IBM Research.
And I'm Dilun Kirat.
And we both are research scientists and AI supply chain security. And in our team, we're using a lot of the AI technique to improve supply chain security. At the same time, we're also looking into security of the AI, and those are the issues we're also looking into it.
So actually, back in 2018, in this very stage, we presented Deep Locker, which is about how bad actors can use AI and ML to create advanced threats. But today, we'll be talking about how some of these advanced attacks can be detected using same AI and ML technology, specifically in the software supply chain scenarios.
All right, so hope you guys enjoy our talk. So let's jump in. So suppose that I'm a software supplier and I develop maybe a great tool because this is vacation season. I create software to plan your awesome summer vacation, find the best deal. And I maybe assign those binary with a valid certificate and provide all the list of dependencies I use and develop this software. And if I give to you, maybe do you trust and use it? I already know the answer, and it probably is highly likely depending on how much trust you have to me as a software supplier. And this question or this observation is not something new, and also it was highlighted by Cam Townsend, his famous Turing mode lecture about the reflection on trusting trust. So basically, unless you create a software from the scratch by yourself, including source code and compiler, and you cannot simply trust it. So it's a matter about where we have our trust in the software. So most of the time, that's why we rely on software supplier vendor and their reputation, their development history to trust software. Which is great, but until they break, may be broken. And that's why the supply chain attack happening. So you may remember SolarWinds that has hit all the media and that affected a lot of organizations, and that has happened from malicious code injected in software update process. And also similarly, in the Kaseya cases, software update process got compromised such that it used to distribute a lot of the ransomware. And this happened a lot of in the commercial sector, but it also happening in many of the open source projects. And you may remember there is dependency confusion research, which is about sorting and maybe same the package name present in private and also public kind of the repository. And there will be the dependency confusion. So there may be, in the end, you may use incorrect packages, not something you intend to use it. And also protestware cases, popular NPM packages in one day maybe just turn into the wiper, and they just destroy all your file. And recently, of course, we all know about CrowdStrike, which is not a cyber attack, but that also highlighted when our trust on the software vendor and software update is broken, that there will be massive consequences happening, and that may affect our day-to-day life. Let me recap one of the most recent examples happening in the open source community, which was quite major happening, and we see about exit backdoor. About 4 months ago, there was interesting observation was posted OSS security. And there has been some suspicious activity, high CPU use happening, SSH during the kind of the var grind, kind of the debugging. And that triggers deeper investigation about this issue. And it turns out that there could be a backdoor in XC library that can lead to SSH compromise. So this triggered the whole investigation about this repository. And then they discovered 2 to 3 years of whole supply chain attack happening, very sophisticated and very interesting in many ways, and to highlight the supply chain attack happening in many of the popular software. And if we don't know about the XG, which is kind of compression, decompression, the library, and the tool, the reason people have attention on this problem is that XG or libLZMA is part of the dependency of the system D. Again, system D is a dependency of OpenSSH, meaning that if the bad actor has the correct private key, they can take control of your SSH server remotely. So it sounds quite disaster. So that could be major impact. And during this investigation about the exit backdoor, it discovered many interesting aspects about supply chain. For example, this bad actor created multiple identity such that they give the pressure to the original maintainer, because open source, in some sense, kind of voluntary work to make sure to maintain it. And of course, they have their day-to-day job, and that's why maybe the patching, releasing might be delayed. And they using that factor to pressure the original maintainer. Hey, you guys slow, so you need to accept this guy, the new guy, as another maintainer. So in the end, this new bad actor become a maintainer, now have the full control. And over the time, this guy introduced a lot of the stealth technique to hide a lot of the malicious code, like obfuscation, and then multi-chain kind of the payload construction. So if you look at the source code, it may not be obvious to find all this malicious code. So this case and all other supply chain attack highlighted there is clearly semantic gap between actual the code we expect as the behavior from the code and the metadata you get it. Let's step back and look at maybe supply chain, how the software supply look like. And 10,000 foot level, developer develop source code and build a source code, build a compiled code, and then deliver to the end user. And end user, of course, they use it. And there has been a lot of study, research, tools, standard to protect many aspects of software supply chain, like finding the vulnerability to improve security and to ensure the integrity of the CI/CD pipeline, and a lot of standard to provide assurance about the provenance, which is all great standard, and there is a lot of the research community effort happening here. But as a security researcher, we always need to think about what would be the worst case scenario, what would be the consequences. So as highlighted in SolarWinds X backdoor, their development chain got compromised, that can affect actually the release. And how about the maybe compromise, stolen certificate that happened many times in highlighted in many media, and the reproducible build is great concept, but it's really hard to execute in many cases. And also SALSA is a great standard, but SALSA version 4 requires a lot of human effort, and so SBOM is providing ingredient, but now it's a burden to the user to verify complete correctness. And also it's highlighted in Log4j, maybe some of you support during your vacation time, maybe that was 3 years ago. So Log4j, when it happened, we need a quick way to find out where this vulnerable piece of code. So this all highlight there is still gap, there is room to improve in this supply chain. And in this talk, we are going to focus on right-hand side of the supply chain, because most of the time, the user only get the executable binary. And the only way to trust the executable binary is they have to trust software vendor. But as I highlighted, many of supply chain attack, if that trust is broken, there could be the massive consequence happening. So that's why we develop Code Genome technique, and then using this, and we want to help the user to help to improve supply chain security, and so without trusting the software vendor, but they can still trust the software. And I'm going to hand over to Dilung, so he's going to go into technical detail about Code Genome.
All right, so thank you, Jiyoung. So Code Genome, what is this, right? So before diving into the detail, let me quickly revisit the problem of unknown software, right? As we discussed, software usually comes with metadata along with the code. Metadata, what I mean by that is simply the file name, or more advanced, like the hashes, or signatures, or SBOMs. And this basically tells what the software is and what it does, right? And we build trust by verifying this metadata. But the true behavior of the software entirely depends on the code, the supplied code, not the metadata. The metadata may say something. The hashes and signatures checks out. But when you actually run the code, it can do some completely different things. So here is this inherent semantic gap between metadata and code that I've been describing. And this is the misplaced trust in the metadata that actually one of the root cause of a lot of the problem in software supply chain. So how can we bridge this gap? So the one option would be to actually look into the code. If you, are an expert in that, you can reverse engineer, determine exactly what the code is doing, and then realize whether it aligns with the metadata or not that describes what the code is supposed to do. But for average consumer, it's not scalable, it's not practical. And then what we're proposing is a differential analysis way of solving this issue. And what I mean by that is, let's start from some good known state, maybe some previous version of the software that is known to be safe and the metadata is accurate. So what we're going to do is we're going to look into the code and whether their computational semantic is the same, right? So that's where the Code Genomes comes into action. So Code Genome Framework allows us to extract semantically meaningful fingerprint from this code that we're calling Code Genome. And then we can compare these genes, and then if they are all matches, what that means is these two codes are functionally similar. So with that, we can also extrapolate that the metadata that is coming from the trusted code can be applied to this unknown code that just came in, right? So that's the high-level idea. But if we look into this, what is happening here is we are building the chain of trust, not by simply trusting the supplier, not by simply trusting the metadata, but we're building the chain of trust by truly following the code equivalency. So this is, we think, is one of the ultimate way to bridge this semantic gap. All right, so how does the code genome work, right? At high level, so obviously we start from code, that's what we get. And of course, we do the disassembly to find it into individual functions. So then we're going to lift it into IR, intermediate representation. So I'm going to talk why we want to do this. So once it's in the IR, so we're going to do optimization and generalization, and what we're calling it the canonicalization process. And ultimately, we get this canonical IR version of the function. And after that, we're going to apply, there are multiple tools that can extract embedding from this canonical IR. And the Code Genome Framework allows us to pick and choose different tools, because each of these states, there are multiple tools available. Some of them are open source, some of them are proprietary, and based on the use cases, some of them may work better. In certain cases, other tools may work better. So the next, we're going to look into how it's implemented in our current form. So first, of course, we want to extract all the functions from the code. That's the disassembly. And then the goal here is for each function, we want to compute this code genome that captures the essence of the functions, the behavior of the function. And turns out, usually, that means the code of the function, right? But not just that, it also depends on the data. A lot of the behavior of the function also depends on the data. Sometimes entirely depends on the data more than the code. And also there is, sometimes the function calls other functions. So these are also needs to be part of the genome of that particular function. So with that, what we have concluded is as an ingredient for an individual gene of a function, we're going to take three components: the actual code, the data that it depends on, and the functions it calls. But of course, if you include all the functions and its code, it's not tractable. So we are only taking the definition of the function. So after that, as I said, we're going to lift it into IR. And in this case, we're using this open source tool called retargetable decompiler. So it's based on LLVM IR. So of course, the IR, the intermediate representation that we're using is in LLVM IR format. So once we have this LLVM IR, so we're going to go ahead and do the canonicalization process. So this is implemented in the LLVM path. So basically, there are two stages. First is the optimization. So here we're leveraging the large number of research work that has been done in the past multiple decades on the compiler optimization. And this passes, what it does is, given a function, it tries to find and reduce the function into the essential components that is needed to do the computation that is supposed to do, maintaining the equivalency of the code. So once we pass through this optimization, so there are also other passes that works on generalizing the code. For example, first, of course, extracting all the dependencies, global variables, structures, also consistently renaming, and also consistently sorting data that are dependent. So in the end, what happens is that for each function, we have this, what we call the shadow module, that is independent but complete in a sense. It contains all the things that is needed for that particular function to behave the way it's supposed to behave. And that is the component, what we're calling the canonical IR. And after that, we can use that as the starting point to extract the actual embedding or feature vector or genome that we're calling. So in this case, we are using Sigmal. So Sigmal is based on a signal processing based approach, where the canonical IR is converted into image and then use some Gabor filters to extract ultimately the feature vectors, which is the ultimate gene here. So let's take a quick look at a concrete example. In the left, so there is the machine code. I'm showing also the code so that you can have some comparison there. But of course, we start with the binary code. But we can also start with source and directly lift to the IR with the LLVM. So once it's lifted to IR, we're calling it raw IR. So after that, it goes through the canonicalization process that generalizes things. It removes some of the instruction that may be not needed, or reduce some, make it more optimized to the minimal form of the function. So once we have this canonical IR, so we're going to convert it into bitcode, which is the binary form of the IR. And then since we are using Sigma in this pipeline, so it converts into bitcode image and then extract this embedding as a code gene. All right, so with that pipeline, let's look at a simple example. So here we have 4 binaries. And assume that each binary has only one function. And they look completely different at the binary form. I'm also showing the actual source code so that you can inspect that as well. But if you look at take the hash, they are different. If you start doing, a mnemonic n-gram, they will be completely different. But if we go through the pipeline that we just described, turns out they all generate the same gene. What does that mean? That means these all functions or these all binaries are computationally equivalent. And with that, so let's assume that there is this metadata that is assigned to the smaller function, maybe by actually looking at the code and verifying, okay, this metadata tells exactly what the code does. The code basically does is, given any argument, it's just going to add 32. So with that and with the code equivalency, now we can apply the same metadata to all of the other binaries. And the key fact here is that to be able to do that, you don't have to reverse engineer all this complex code or complex binary. You can still confidently apply this metadata to all the other 3 binaries with this process. So that is the idea of Code Genome here. Of course, it looks good, but of course there are like multiple advantages and also challenges. One of the main advantages, especially using the LLVM IR-based intermediate representation, is that it can support multiple architectures, multiple compilers, multiple optimization levels. It can handle a certain obfuscation. For example, basic block. If you are shuffling the basic block, it will represent differently in the actual binary. But once we go through the LLVM IR, you can reduce it to the same gene. But there is also challenges. These are coming from the classic challenges with any binary analysis. Like it's generally accepted that disassembly is undecidable. And because of that fact, the function boundary recognition can be challenging. Sometimes functions can overlap. And also, since we are moving into the IR, there is also a loss of architecturally specific nuances that might be interesting or important to actually capture the gene. And finally, the canonicalization process, we're trying to recover some kind of high-level abstraction of the code, and there are also some limitations how much we can do with that. So with that challenges in mind, what we want to see next is how it actually fares with the real-world challenges, right? And for that, I'm going to go and do the demo. So the demo is about uncovering some supply chain attack. And as you might have guessed, it's about the XG backdoor that Gio just explained. And we saw that to get to this backdoor, the miscreant was spending many years and very elaborate way to introduce the backdoor. But the fact of the matter is that the backdoor has to be there in the final binary some way, somehow, some form. And in this demo, you'll see we only care about that. We don't care about how complex the whole process was. I mean, it's very interesting. It's a nice story. But ultimately, what it matters is the code needs to be there. And we're looking at the code to see that. So what we're going to see in the demo is there are 2 binaries, right? So one, I'm going to compile from pulling the code from the source from the GitHub. And the other binary is distributed. In this case, Debian distribution. So we're going to generate genes from these 2 binaries. It's coming from the same source code. At least it's supposed to be coming from the same source code. It's the same version. So we generate 2 sets of genes. Since these genes are basically embedding vectors in high-dimensional space, so we're going to project them into that high-dimensional space and see where they land. And then usually, this gene will find the pair, but some of the genes might have no pair, and some of the genes might be not too close, right? So this is what we're looking for with this demo. So let's switch on to the demo. So here, what we're seeing is in the left is the Code Genome UI, more specifically the GeneDiff UI. And in the right, I have like 2 sets of binaries. So each set is representing one version of this coming from the same source. So one I'm compiling from the GitHub repo and one coming from the distribution, right? So we can go ahead and drag and drop these 2 binary. First, I'm going to start with the older version, which was the version is known before the backdoor was introduced, right? So I dragged and it's processing. It's in real time. So what's happening in the back end is basically going through the pipeline, Code Genome pipeline, lifting to disassembling, lifting to IR, canonicalization, generating gene, and comparing that. And then, yes, now we have the result. And the result shows the more interesting part is it's 100% similar. All the genes are similar. And that is to be expected because the source is the same. I'm compiling myself, and one is coming from the distribution. The hashes are different because they are compiling a different build environment, but the genes are the same. So let's try to do that, the same thing with the version that is known to have backdoor. All right, so in this case, I'm going to use Hollywood Magic, and I'm going to speed it up. But basically, in the left is the GitHub version that I compiled, and then in the right is going to be the distributed version that came in the Debian package. And it's processing, and now we have the result. And now the difference, right? So now you see the gene similarity is only 70%. There are quite a few identical genes, some similar genes, but it also has like 101 additional genes, and also some mismatches. And this UI allows us to also inspect inside each of these gene pairs. For example, we can look at some similar genes first to see how it looks like. So I'm picking up the first pair, and when we click the compare functions, we can first see the actual binary. So that is showing the assembly. There are quite a few differences, highlighted by red. And these are because of the result of the introduction of the code of the backdoor, and that is replacing some of the function relocation happening there, and that is changing the actual code. But the actual computation that the function is supposed to do is exactly the same. But this also highlights, if you only look at the binary, they are quite different, right? There are many differences. But once we look into the LLVM IR version, which is going through this canonicalization process, so it should only show very few, only 2 differences. It's very minor differences. It goes to show that the importance of doing the canonicalization to reduce the functionality into the minimum set. So the next most interesting part is the mismatches, right? So I'm now filtering only the mismatch functions. So there are quite a few mismatch functions. So one of them actually has a low number. I don't know if you can see, but it's 95. So I'm going to check this out. So it's called the CRC64_result. So if you look at the comparison, so it's completely different. So remember, this is coming from the same source, and you compile just the 2 different environments, and then the functions are completely different. Turns out, so this is one of the key component of the XG backdoor that's utilizing this indirect function call in the glibc to surreptitiously change the behavior of the function. And of course, that also reflects in the LLVM IR version of these functions. So here, this is the UI version of the tool, but many of us in this room might also appreciate having a command line tool. So this is what we're saying, like the same analysis doing with the GeneDiff, but through the command line, and it generates the same result, but now we can go through finding similar genes, like mismatch genes, and it's outputting the text. But this command line version has also some additional capability so that we can see, for example, changing the threshold or changing the output format, for example, like JSON file, and that you can use to further down in the downstream task to do some detection or some CI/CD pipelines. So far we checked 2 versions of the binary, right? But what if like we look into all the other versions? So there are like so many other versions. What would we see as an insight? So that's exactly what we did. And this is the graph. So in the y-axis is basically the gene similarity, and then x-axis is all the versions that was released for the XG library. And as we expected, they are all 100% in the early part. But suddenly, the version 5.6.0, which is the first version where the backdoor was introduced, so suddenly we have a very low similarity score. And then the other version, 5.6.1, has also a very low similarity. And that was the one we saw in the demo. So this highlights to show that, of course, it's always, obvious and easy to make this argument, after the fact. But if we have been doing this analysis, we would have detected this anomaly. And to be honest, this is not too expensive. You only do once for one release. How many releases is happening, over the year, right? So it's not super expensive, and you can do this for all the important open source projects. So that's what we hope that it will happen. And the other thing I wanted to point out is it also shows that, usability of reproducible build use case. Like we are seeing 100% similarity, even if the binaries are different, in the hashes are different because they're built in a different build environment, but you can still kind of guarantee that, they have the same functionality. So that also, this code genome can be used. So this is a very unique case of, introduction of backdoor that was only present in the distributed build. But what if it was present in also in the local build that I was building? So what about that, right? So can we cast that kind of changes? So for that, the other approach we're proposing is like we're going to do incremental version analysis, meaning I'm going to compare the current version with the previous version and how much code changed. So that's what we did. And in this graph, you can see the early version has a lot of changes. And that's because it was coming from 2007 to 2009. These are all alpha and beta builds. There were a lot of changes happening. Probably the project was quite new. But after version 5, the gene similarity is quite calm and stable, right, for decades. And suddenly, in 2024, there's a huge earthquake. And now it's going up and down. A lot of changes happening. And this is also could have been used to detect some anomaly there. And then, of course, we need to inspect what's happening there. But it's clearly it's an anomaly. Over the decades, it was quite stable. And suddenly, there's a lot of change. And turns out, like, what caused this earthquake is a very simple commit that says adding some test files, right? So a test file is not supposed to change your binary, the final binary. It's just for test. But somehow it's changing it. And that's also another red flag you could have seen beforehand. All right. So far we see, we're looking into individual binary or binary pairs to do analysis using Code Genome. But the actual software ecosystem is quite complex. It comes with the packages, complex dependency chains, and then it's very hard to navigate the security problem in that space. But what we believe is that the fundamental capability that the Code Genome provides can be used to tackle some of the use cases there as well. And Jiyoung is going to explain how we can do that next.
All right. Thank you, Daryl. I hope we don't see what happened at the keynote. So I hope we have proper screen. All right, so as Dylan walks through the Code Genome technical detail and demonstration, so we believe the Code Genome Framework can help to improve the supply chain security and supply chain, the pipeline and ecosystem. And whenever we talk about software supply chain, of course, one of the most important standard or popular standard people discuss is SBOM, Software Bill of Material, which was also highlighted by executive order. So SBOM at the high level is quite simple. So it provides all the list of ingredients or the list of components the developer use to build some software. So common analogy people doing is when you buy a cookie from the store, when you back up the envelope, you see all the list of ingredients they use to bake this cookie. So similar concept for the software, which is really great concept so that they give the confidence for the end user, okay, I'm getting software X, but the software X using XYZ or something internally. So you know which version of library using it or which license of code being used to develop the software. So you can do the maybe compliance check, security vulnerability management. There's a lot of the use cases you can build on top of this one. But again, the problem is that SBOM is one of the metadata. And as we highlighted multiple times, so if the the trust for the software vendor or metadata is broken, there could be a gap and issue. And again, that will be the case in SBOM. So that's why we highlighted we need to trust, but at the same time, we need a way to verify its correctness and completeness. Because each vendor will provide SBOM. In the end, you may see some JSON file, XML file, SBOM lists all the ingredients, but the user, do they have the proper way to verify its completeness, correctness? So what I mean by that is, when you get the SBOM, it lists all the ingredients or the library they use, but what if the developer made a mistake? So maybe instead of version 1, it says maybe version 0.9 or maybe 1.5 or something, so maybe the version mismatches. Or sometimes if the developer, and this is something that also highlighted in the previous Black Hat talk, and some of the vendors is using the GPL license code, and of course clearly they have the motivation to hide the presence of the library to avoid any legal issues. So they may intentionally omit some of the library in the SBOM. So that's why there could be the issue of correctness and completeness of SBOM. So that's why the user needs a way to verify the correctness and completeness of SBOM. And on the right-hand side, you see some of the simple Docker file. And we actually try some of the SBOM generation tool on these two Docker images. And the first one is quite simple. Ubuntu image, you install wget, and when you inspect the SBOM as expected, it lists the wget, which is obvious. But on the right-hand side, the minor difference is that now we remove the dpackage database, which is used by aptitude. The meaning that, so now the aptitude doesn't have any information about the wget, even though the Docker image actually has the wget binary. So when we try the SBOM generation on this Docker image, surprisingly or unsurprisingly, there is no wget in SBOM. What does this tell us is, many of the tools, they use the metadata, in this case, dpackage database, to generate the SBOM. The metadata is a great source to boost, to collect all the ingredients, all the information, but that could not be the only information you have to rely on. So again, we have to trust, but at the same time, we need a way to verify. Otherwise, there could be the gap. And that's why using the Code Genome technology, what we are doing is we are building large-scale knowledge graph in a cloud infrastructure, and where we are ingesting large scale of the software into the knowledge graph. And most of software, of course, when you Debian, some common distro, you get a package. And inside the package, of course, is multiple layer, like you have maybe multiple archive file, could be some of them code, some of them could be the data file. And inside the file, as Dylan mentioned, we are going all the way down to the function level to extract the gene. So this process, we are doing all the file from the trusted source and then building the knowledge graph. So from the package, we unpeel the onions to going into the archive file to the each of the function and generate all the gene. And we do all this process, all the incoming packages, and then we build a large scale of the knowledge graph. And what we can do is, whenever we have new packages, we using the gene similarity, finding the matches, and then using the chain of trust, which Dylan highlighted, we can find and we can identify which package, which component inside of these packages. So by building the knowledge graph, we can identify the software component, and then we can use the technique to verify it. So the next part of the demo, I'm going to briefly show how we can actually generate the SBOM from the unknown RPM packages, which could be quite challenging because if the SBOM generator simply relies on the metadata, and we commonly observe, we often observe some of the tools, they use the exact hash of the RPM packages because when you go to the Debian or maybe the CentOS, those RPM or the Debian packages is quite stable. So that's why they're using the hash matching to identify what this package is, which is quite effective and quite fast. But the gap could be if someone give you the custom RPM packages. In this case, we create a random RPM package by mixing different binary and then see whether our code genome actually can identify inside the ingredient. So that's what I'm going to show in action. All right, so similar UI as Dylan showed. So here, we are going to upload the unknown RPM I just mentioned, and RPM package, upload, and then this is unknown RPM, intentionally made as unknown because we don't want to give any metadata information to the system. And then in the behind the scene is start processing it. And again, Hollywood magic, I just speed up for the sake of the time. So what you see is, of course, high level information, file size, file type. But what is most interesting is when you unpeel the onions, you find all the layers, so like how many kind of files inside. Well, some of them could be data files, some of them the documentation file. But what we are interested in is in SBOM. On the right-hand side, you see the SBOM JSON format. In this case, this is in CycloneDX format, one of the CycloneDX, SPDX common format. And this JSON file we can download, and that can be used for any downstream task integration. So we just download it. I'm going to using that as second part of the demo. And here, so this is summary view about the list of the ingredient or component we found from these packages. You can see on each of the row highlight different binary that was identified from these unknown IPM packages. It shows the version, size, file type, and even package URL. And this is another open source from the community from the dependence track, where you can upload SBOM. In this case, I'm going to try to upload SBOM. I just download it, and that can be uploaded to the system. And then the nice part of the dependence track is you can manage many of the software and their ingredient. And another benefit is this dependence track comes with a lot of the data connector. So for example, you can connect to the CVE, and then you can find maybe if some of the component has a known vulnerability, you can associate the CVE. So that's how you can manage and maintain all this the software. So this is great capability, but this is not the only application we are envisioning. So by building large-scale knowledge graph using Code Genome technology, we're trying to support many different use cases. By following the chain of trust we described, we can do a lot of very interesting use cases we can support from the knowledge graph side. So for example, maybe some new CVE vulnerability find out, we can find by following chain of trust, we can find other code that may share the same type of vulnerability. Of course, code similarity doesn't always guarantee this is buggy code because their bug may be across many different files, a lot of complexity is happening, but at least this could give you an early indication about there could be potential issue. Maybe we want to prioritize it. And also, as you highlighted SBOM generation cases, we can also use that as a classification or component identification. And also, by using the similarity that has been sort of many malware analysis community, we can try to find the backdoor. So these are just few of the highlight examples, but you can imagine many of the other interesting use cases using this technology. So as I highlighted during the presentation, we believe Code Genome knowledge graph can really help to improve software supply chain security. That's why we decided to open source our Code Genome Framework so that we can work together and that we can also foster bigger collaboration across community, because there's a lot of software out there. When you look at the open source, it's huge, and it's not something a few people can do it. So that's why we are open source and invite other people to work together to tackle this issue. And by open sourcing it, we believe this can help the bigger collaboration among the community and then start tackling the bigger issues in supply chain security.
So about the open source, so it's actually already out there, public. It includes two major components. The first one is the Code Genome Framework itself, and then the JAudit, which is used for supporting jar files and Java files for the genome extraction. So for the Code Genome Framework, we have GeneDiff that you saw earlier, the basic knowledge graph that is needed, some CLI tools in the UI, and it supports most of the common binary format and architectures. And it also includes the optimized version of the canonicalization. So here's the link. Please check it out. It only requires, after you git pull, git clone, only the make starts. There's one command, and a few minutes you should have this UI you can test with some of your use cases. So then for next, we also want to support the packages like RPM and others, and also the different archives that you saw in the second demo, which is already present in the cloud native version of the Code Genome. So that's also what we hope would be able to open source.
So at the very last slide, we are going to give you QR code, so don't worry about the link. So to conclude our talk, these are the three key takeaways. So as we highlight in many of the supply chain attacks, so there is clear inheritance semantic gap between the code and the metadata.
And then now the open source Code Genome Framework, we believe, can help bridge that gap.
So we believe by open sourcing this framework and then using the Code Genome technology, we can improve the supply chain security issue together. So with this, we are going to conclude our talk. And again, these are the QR code to our repository. And thank you for your attention. And due to the time limit, I may invite the people to the room to discuss any offline conversation if anyone has any follow-up question or interest to talk about the future collaboration, we are happy to talk. So thank you for your attention. Thank you for coming.
Thank you.